All right. So anyway, we got a couple of minutes anyway, and I saw some interesting news. The world is ridiculously exciting. This guy Caputo was big in Trump's team, and he seems to have gone completely insane. He recorded a video saying that the shadows on the wall are coming after him. He thinks his mental health is shot. He's been working at the Health and Human Services. Trump got very upset at the doctors saying that his complete lying about the coronavirus was not okay. So he's been vigorously replacing all the executives at all the medical services in America. So they're with political people who will publish lies. So they published the lie that hydroxychloroquine worked. And that's what Caputo is. Caputo is basically a KGB political orthodoxy officer, making sure that the medical statements from the scientists are whitewashed and turned into the political statements that support the Trump agenda, which is kind of hard since Trump changes what he says every day or two. Like he said, masks are good, then he had the rally without masks. But anyway, Caputo seems to have completely gone insane and posted crazy things. And he said that he's afraid there's going to be a civil war in America. And after that, Biden will win and the Trump supporters will have to bring out guns and start shooting people, shooting all the liberals. And I heard an interview with the reporter that said this, and she said, it was Rachel Maddow. She said, this is really crazy. And she said, well, actually, this is pretty common stuff for Trump's inner circle. Most of them think like that. So anyway, it is rather terrifying. And here's another guy from the Trump inner circle, Michael Schauer. He was actually in the CIA and hunted Osama bin Laden, and he has now decided that American liberals and Democrats are just as bad as Osama bin Laden, and you should all get guns and just start shooting them. And he's been posting this. He's pro-torture and stuff. It's just like Trump. And a lot of them are talking about this nonsense. So, you know, it really is getting kind of scary. And the thing that I wondered about, I watched this is following exactly what Hitler did, where he takes over the government. Now, the thing that's happened in the last month, which is a real sign, is that he starts openly breaking the law. Like it was absolutely illegal to have the Republican National Convention at the White House. And Trump might be above the law, but the other people around him aren't. But nobody even bothers to prosecute him because we've all just accepted that he will just break the law and we'll do nothing about it. And his last rally was illegal, the indoor rally without masks. And the thing that I expected after that was the Hitler Youth. And I wondered where the Hitler Youth were, because that was a big step of Hitler's thing, is when the teenagers got brown uniforms and they all marched around making an armed militia to support Hitler. And Trump is talking about that. And now I see it's really happening. The adults are doing it. And the big thing here is the Q hoax that Antifa terrorists are setting the fires. So they had these people all over, including real law enforcement officers with them. Well, the Boogaloo Boys are a little different, but yeah, it's similar to it. But the thing that got me is this guy, Turning Point. This guy was the keynote, the first speaker at the Republican National Convention. And he has a troll farm of teenagers that are paid to spread Trump propaganda on social networks. And I think they're the modern analog of the Hitler Youth. So we're really just following right down the standard step-by-step decay into an autocracy. So, you know, nothing's more important than next election, which they are vigorously trying to rig in really big ways. There's a lawsuit about the release of fake documents from the post office to tell people false things about how to vote. And I saw another thing on Twitter, I didn't see it in the main news, that one person said, when you actually get your absentee ballot application in states where you must apply, not California, it's covered with pictures of Donald Trump front and back. So it looks like a Donald Trump campaigner. So if you're not a Trump voter, you'll just throw it away and not realize that it's your ballot. So anyway, they're also talking about getting people to hang out at the ballots and at the polling places and try to intimidate voters. So, you know, we're in for an exciting time, like a country in great unrest. Anyway, I got IBM homomorphic encryption running, which is, I went to the IBM training today, and this is interesting, but it is incredibly slow. I think this is about 1,000 times slower than doing calculations without it. So it is not really ready for prime time at all, I'm afraid. Anyway, but more about that in the cryptography class, which is on Thursday. So here we are in malware analysis. And the first thing I want to do is talk in more detail about OllyDbg. And then I'm going to show you a little more OllyDbg, but the main thing I want to show you are new things I've done, the Flare VM and WinDbg. So more about that coming. Anyway, so let's start with the stuff from the chapters. And that's here. So make this as big as it's going to get. Okay, so here's OllyDbg. And I already started using it last time ago. Well, it's been around for a long time. It only does 32-bit programs, which is a really serious limitation. Now, the old version, OllyDbg 1.1, is a favorite for hackers, and that's what we're using here. Now, OllyDbg 2, I got angry at it because I couldn't find these two modules in it, but a Microsoft engineer watched this class and emailed me and told me that that's okay because these modules are not independent modules. They're just aliases pointing to other modules. So in fact, OllyDbg is correct not to show it to you. But anyway, most people don't like OllyDbg 2. And OllyDbg 1.1 is the nice one. So you can load executables directly and run them inside OllyDbg like we did last time. You can also load libraries directly into OllyDbg. Executables, you just open them inside there. It'll load in the debugger and stop. Debuggers always work this way. When they load a program, they stop it because presumably you want to examine or modify it. You can also attach to a running process. If you have something already running in the background, you can attach to it, and then it will pause the process with a breakpoint. Then you'll see what's going on in there. Right, you can reload a file. There's nice function key shortcuts in OllyDbg. F2 sets a breakpoint. Control F2 reloads the executable, and you can do all these from the menu also. So anyway, you have the disassembly pane here, which shows you the disassembled source code and the raw hexadecimal bytes that make the instruction and the address. Then you have the registers over here. The top is the main stuff we care about. EAX and ESP and EBP, the top and bottom of the current stack frame, and EIP down here on a separate line because that's really important. That's the address of the next instruction to be executed. Then you can dump memory here, and you can see the stack here, which appears in 32-bit words. And if the address in that 32-bit word points to something that OllyDbg can understand, it will tell you what it is. So this is a return to the kernel, and here's a return to ntdil. Here's the end of the structured exception handler chain, and so on. So that's the nice thing about Olly. You get a nice graphical environment. You don't need to type in command line tools, command line commands and memorize them. You can just pick off a menu. That's why people love it. So you press space, you can disassemble and change the code, and you can modify the contents of the register, and you can dump any area you want, follow and dump in the. So it's very nice. Now the memory map is one of my favorite things. It's helped me understand how memory is used by Windows code. You open up the memory map and it just shows you all the memory segments that are used by your program and what they are. And so for example, here I was running one of your lab samples, lab 0901. And so you just have a portable executable header and then code, imports, and data. That's all there is to that one. And down here is a user library from Windows, and here's a shell. So each item that is running in memory is shown here, and not only does it give you the name of it and the address where it starts and ends, well, the start and the size, then it tells you what type it is and what access is allowed there. And you might notice that you can read all of them. They all have an R. Some of them you can write with a W, and some you can execute, but none of them let you write and execute at the same time, which is a fundamental security model of Windows. You're not allowed to have write and execute in the same segment anymore in Windows. You can, in fact, create segments like that, but no legitimate software will create them because those are dangerous. Those are areas where you could modify the data and then execute the modified data, which we do a lot of in the exploit development class. So rebasing, you notice each module has to live somewhere. Your main program always starts at 400,000, and all the other modules have to be somewhere in memory. And the whole point of address space layout randomization, which is in all modern versions of Windows, is every time you reload something, it moves to a random physical memory location, and it might have a virtual memory location where it internally thinks it's at 400,000, but it isn't really. It's located in a random part of memory. So if a module cannot load at its preferred base address, which would happen if you have two libraries that both have the same base address, then they have to relocate the library file. In principle, it could happen to executables also. And so DILs are more commonly relocated. Windows DILs, Microsoft is smart enough to assign each Windows DIL a different base address. So they can usually just load in their preferred location. But the third-party DILs might all have the same base address, and then there'll be a collision, so they have to relocate it. And that's done with the relocation section. It therefore takes a little longer to load. All right, so anyway, here you've got absolute versus relative address. If you try to relocate this code, these commands refer to the memory inside registers like EBP and EAX, so that would be fine. And this jump not zero refers to an absolute address, but it's not really a literal absolute address. This is just the disassembler telling you where it's pointing. A jump not zero is actually relative. It will say just jump forward 50 bytes or jump backward 100 bytes. So these instructions can be relocated anywhere in memory and it will be fine. But here you get the hard-coded problem. This is why they call this hard-coded code. If you deliberately refer to an explicit address in a command like this, which is referring especially to that address, then you can't relocate this code. If you move it to another address, that address will be wrong. So when you rebase the code and move it to another address, you have to find all the instructions with hard-coded addresses and change all the hard-coded addresses. That's what happens. There's a relocation section, which is a list of all the fix-up addresses, and that's the point. That's why you have a relocation section in most code. So here I've loaded something called metadarcer.dil. I guess I got it from the textbook. But the point is you got text, data, resource, and this relocation section. It's not always there, but if it's not there, then this code cannot be relocated in memory. Anyway, they call that rebasing. And you can remove the relocation section with a tool like LordPE. And then this library can no longer be rebased. But that would mean that if you already have that memory in use by something else, I think the thing would just crash and put up an error message. I haven't tried it, but it certainly couldn't do that. So here's DIL rebasing. Here's two DILs with the same location. They both want to be at 100 million. Of course, this is hexadecimal in case you care, so it's not really millions, it's something bigger. But anyway, DIL A and DIL B both want to be there. DIL A apparently loaded first and got it. DIL B had to be relocated to 340,000 instead. So it will have used all the addresses in its relocation and rewritten the code in memory to make it run in that other address. All right, IDA Pro does not know about rebasing. This is a problem with reverse engineering tools. They typically try, just like we mentioned before, if you do dynamic analysis of malware, you run it in a virtual machine, and that is not really the same as running it on a real machine. And sometimes the malware will notice or run differently. And the same thing's true of your tools like disassembly and debuggers. They attempt to simulate a running machine, and they make some assumptions and some guesses, and so they're not perfect. So if you use OllyDbg and IDA Pro at the same time, you'll get different results. OllyDbg is actually connected to a real running process in your machine. IDA is calculating the addresses of stuff that is not running, and it doesn't know about rebasing. So that's a fairly common issue if you try to compare the output of the two tools. All right, so you can view threads inside Olly, and you'll see all the threads. Microsoft Windows is a multi-threading operating system. Not only does it have many processes running at the same time, but each process is broken up into smaller code pieces called threads. And the point of threads is the threads can move forward independently. So if one thread stops because it's waiting for something slow, like user input, the other threads can keep moving. And so you can view individual threads in OllyDbg, although I've never had to do that. And each thread has its own stack. So here's the stack of thread 2, the stack of thread 3, and so on. So that would work if you want to analyze complicated modern programs. I only do small little malware and capture the flag contest code, but if you were to really try to analyze something complicated, you'd have to deal with that. So here's your code execution. F9 will just run, the same as clicking the run button. That will start running the code, and the code will just run. It'll pop up menu boxes, do network connections and everything. You can pause it here, although that would be kind of strange because programs run so fast that if you hit pause, it's not clear where you're pausing it. You can run to the selection where you choose a location in the code window with your mouse and then run there. Run till the next return, till user code. And here's the ones I use more often. We'll use the Alt F9 in the exploit development class where you let the debug go. Anyway, here you can step into is what steps into, it moves to the next instruction, even if the next instruction is in a different module, because the one you're in now is a call. Then it will step into the thing that's called and start debugging it. Although, if it steps into the kernel, OllyDbg is not capable of debugging the kernel. The only thing it can really do is a step over, where it runs the code until it returns. But a step over is usually what you want once you're in the level of hierarchy that you're interested in analyzing, like the code written by the author of the malware and not all the library code written by Microsoft, and you step over the function calls to not waste your time trying to debug Microsoft code and focus on debugging the code written by the malware author. That's usually what you want to do, unless you're trying to get a Microsoft bug bounty debugging Microsoft software. And in that case, you really don't want to use Olly, you want to use WinDbg. Anyway, so you can run a program and click pause, but of course, you'd have to be able to see what's going on. It might work for something like a game where you want to pause it when the bad guy shoots at you, and there you can see what code makes that shot move or something. Breakpoints is much more controlled, where you search for a string or something, you find the code that does something, and then you put a breakpoint right there like we did last time. So you can run or run to selected code, and you can execute until the next return. So it will go to the end of the current function, but it won't move out of it. This is how you prevent it from moving up to a higher level. That's not usually the case, but you might have that situation where you want to do that. And execute till user code, that would make sense. So you get out of all the code that is not running in user land. And you can step through with single step. This is actually very useful, and I've used it a lot more in GDB on Linux, but for simple code, it's very nice. You just do step, 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 one assembly language instruction at a time. Then you can get to the point where it does something interesting. Of course, big programs have too many instructions. You have to step through thousands of them, but you can do this if you get close to something and you want to see what's happening in some area of interest. All right, so let's try some Cahoots. This is chapter 9, and I think I've got to open this. Let me see if I've got a place to put the winners. All right. Okay. Okay, 9A, B, and C right here. Good. All right. This reminds me, someone was posting a comment about the Boogaloo Boys. The Boogaloo Boys are kind of funny. There was a thing in, I think, Portland, where the Black Lives Matter people are protesting, and they ran into the Boogaloo Boys, and they, after a brief negotiation, they decided that they agreed, and they marched together. So I don't know if the Boogaloo Boys are exactly pro-Trump. I think they're just like gun nuts or something. Anyway, it's there are so many angry people rioting and protesting now that you get a lot of strange combinations. Anyway. This is OllyDbg. All right, we got 23 people. I think a few more may be coming. Give it a few more seconds. Really unstable. Oh, well, there you go. All right, I guess we can go. All right, what key press sets a breakpoint? F2, you use it all the time. All right. What key press modifies a line of assembly code? Spacebar does it. It's not F9. Spacebar modifies code. We were using it last time, but anyway. When you're starting out, you do it with the mouse, but the keystrokes are very handy after you get used to them, especially in IDA Pro, they're handy. Anyway. And what key press steps over? F8. F8 to step over. And I think, yeah, so it's F7 steps into, F8 steps over, and F9 just runs until it stops naturally. All right, so which one runs until user code? All right. That's Alt F9. Runs in special conditions. I should probably use that one more. Anyway, all right. So I got K. Might be, I'm not sure if I know who that is or not. I got an idea. And if they want their points registered, well, if you guys want your points, you'll have to tell me who you are, but if you don't care, that's fine. All right. Anyway, let's go back here and talk more about this. So breakpoints, we used them. Register votes, tell me who they are. Let me make a note of that. All right. All right, so breakpoints. I've used them before. So the most common type is software breakpoints. And that's what F2 puts on. That's the only kind I've ever used. Then you got, of course, the hardware breakpoints. And good, I see people tell me who they are. We'll record those names later. Anyway, then conditional breakpoints and breakpoints on memory are more advanced features. So you can view them with breakpoints, and then it'll show you your breakpoints. These red dots, these red lines here are breakpoints, and here it lists them in a special window. And these are the int3 breakpoints, which are the most common type. Those are the software point where the instruction at that address, which ought to be 52, is in fact going to be CC in memory. And the debugger knows to replace it by 52 when it's time to proceed past the breakpoint. So here's your software breakpoint and your hardware breakpoint. And then you can make conditional breakpoints that execute some kind of if statement to decide whether to stay broken or resume. And you can make memory breakpoints, which similarly use the debugger to break on access or write only when certain conditions are true. They're really sort of a special case of the conditional breakpoint. So anyway, if you close Olly, it will save your breakpoints. If you open the same file again, they'll be there. So it's saving a configuration file someplace, storing the condition of your debugging. The same thing is also true of IDA Pro. People spend like a whole week working on code in IDA Pro, and they really don't want to lose all their notes inside there. So software breakpoint, one of the many times you might want to use it is if you have a string decoder. So in it'll have this junk is what the string is, stored in the resource section or elsewhere in the code. It's got a string, but you can't read it. It calls the decoder. The decoder is going to decode it. So what you do is you put a breakpoint in the decoder after it's decoded it and before it erases it, so you can find out what it does. And if you do the project in the simulator, Jasmine, it simulates that in a very simple case, so you get to see how it works. All right. So Poison Ivy was an example of this. Poison Ivy was a common malware product used to control Windows XP machines. I don't think it's in use anymore. There's more modern stuff. But anyway, it has it allocates a memory section, and then it loads shellcode from command and control servers. And so you can, now the virtual alloc function is what allocates a region of memory, and that's a fairly common thing, but you could set a conditional breakpoint that will notice if the allocated memory fits certain parameters, so you get the right one. So you put a standard breakpoint at the start of virtual alloc, and you look at the stack. Here's what the parameters called for virtual alloc are. It's got an address, a size, a type, and here's the memory protection. And this one's got execute, read, write, and execute, which, by the way, as I mentioned earlier, is kind of a sign that this is not a legitimate memory allocation being used for legitimate purposes, because you shouldn't have all those privileges normally. So you can make a conditional breakpoint. And here what they did was decide that it's going to flag if the if it's more than 100 bytes being reserved, I think is the point of this. Anyway, that was the way they did it in their book, just look for a certain size, but I might also look for this pattern of permissions as a clue that it's being made by malware and not by a legitimate process. Anyway, then there's hardware breakpoints. These are implemented in the processor itself, but there's only room for 4 of them at a time, and they will then, when that address attempts to execute, it will break. And the point of this is you can break with this kind of breakpoint without modifying the code at all. So if you have something like code verification that checks to make sure the code is unaltered, your code will pass with hardware breakpoints, but it would not pass with software breakpoints. And then you have memory breakpoints, and these are simulated inside Olly. So it will break. I think it actually uses a CC. It breaks, then it comes to the debugger, which then checks the condition, and then if it's not time to really break, it resumes the code again. So you can only have one at a time, and of course it's kind of a risky thing coming back to Python and back. It's got a lot of overhead and might fail. Anyway, and then you can, for example, if you want to find out when a DIL is used, you could right-click the DIL section and set a memory breakpoint on access, and then anytime it tries to execute any of the code in that DIL, it will have a break and let you see what happened there. And that would be one way to find out when it uses a DIL. All right, let's look at the second one here. I can record these names. Give it a few more seconds. I guess that's it. All right, so what system exposes AES to timing attacks? Wait a minute, this is not right. This has got to be the wrong class. All right, what's going on here? That's why. 126.9b. That's where we are. Let's try this one. That other one was clearly from the cryptography class. See if this works. All right, I think it was 13 or 14 we had, so. Well, maybe verse 12 is all we're going to have this time. Apparently so. Okay. Let's see if, these look like maybe they're the right questions this time. All right. Yeah, what's the most common type of breakpoint? There you go. Okay, software, that's it. Okay, good. All right, what's the kind where you can have only one? Okay, breakpoint and memory, you're only allowed to have one of them. Fair enough. And what kind of breakpoint can only have 4? Okay, that's the hardware breakpoints. Good. All right. So let's see. I've got Craig. Okay. Right. And JZDAR. Register, I know who that is. So JZDAR, you might want to give me your full name if you want to make sure you get your points in chat or something. But anyway, we'll carry on. So, all right. And of course, we went through that last time in general terms, but I saw your name. I'll record it there. Good. Anyway, so if you want to load a DIL, so you want to load a library to analyze it, without loading the executable that goes with it, then OllyDbg uses a loaddil.exe program. And this will break at the entry point. We're going to be here later, but libraries, when you first load a library, it runs DIL main to prepare the library. And if it's malware, that's usually where you put the malicious code. So you load, it breaks at DIL main, then you run DIL main. DIL main is what prepares a DIL for use. So I'm not going to demonstrate this one live because I've got some different stuff I want to show you later. But if you can open a DIL directly, open something like a Windows DIL, and then you just run it. And you can't use the DIL until after you reload it and run it once, and then you can load it. And when you load it, you get an opportunity to run the code. So if you hit this drop-down box, you'll see the name of all the entry points of the DIL, all the functions in the library, and you can pick a function and execute it. So this one is calling get server by name. This WS232 is a networking DIL. And so this is doing a DNS lookup. And so you can now load in parameters and execute a library call with these parameters and see what comes back. So you can test your library functions one by one, so you don't have to bother writing an executable to test your library. So NTOHL is the thing I used here. This is what converts a 32-bit number from network to host byte order. And we mentioned this before. If you have 127.0.0.1, the loopback address, it's actually stored like this. That's called network order. But if you were to store it as a number, these bytes would be reversed because Intel is little endian. So this takes you from this big endian form, which is what you must have when you're actually sending it out the network card, to the little endian form. And so you can put the address here, and that's the first argument. You're seeing a graphical representation of the stack here. So that's the first argument. And then you choose the function here, and then you can call it. And you'll see what it does, and it will return. So here, I fed in this argument, 7F001, and it returned in EAX 01007F. So it reversed the byte order. So it's a very simple function to take you from big endian to little endian code. But it's a simple one to demonstrate without too many arguments or anything. All right, and you can do tracing, which keeps track of what's happening in the debugger. So there's different types here, and I've really never used any of them, but in more advanced cases, it's good to use them. So standard backtrace, OllyDbg, if you move in with the step into and step over buttons, you can move back with a minus sign, but this is not as good as, say, the undo in Microsoft Word. It doesn't really roll the whole code back. It just lets you see which instruction you came from. It doesn't load the values from the past, but you can do minus to go back a couple steps and then plus to go forward a couple steps just to see where you were. There is a thing called a call stack, which will show the execution path. This shows you I'm in a function, what function called this function, what function called that function. And this you often see if you go to web pages, especially if they're written with Microsoft software like ASP. When a web page crashes, you'll see the whole call stack there. Back, I think, around the time Obama ran the first time, which was what, 2008 or something, I was checking a lot of colleges for vulnerabilities, and I checked some political games for vulnerabilities. And I went to the Republican National Convention's website, and I just tried putting like an apostrophe in the URL, and the whole page turned into screaming red ASP error messages with call stacks. And I said, well, I think I'll stop messing with it. Somebody will get mad at me. But at that time, it was really sleazy and fragile. They're getting better. Although I think Biden's campaign, their app just got hacked and it exposed voter data. And I think the same thing happened to Trump's campaign this week too. Both of them had security flaws this year. Political campaigns seem to be really made on a shoestring budget in a hurry, sleazily and insecurely, like college software. I think in both cases it's because they really don't have much money to spend on it. Anyway, and so this is the one that I think I already demonstrated last time, where you run this program, it asks you for launch codes, and so I think my dog figured this out before you, and this is the one that is so simple that you can see the whole program in just a few lines of assembler. And so it shows you here the C system calls. It calls put S to print a message, it calls scanf to read a number, and then it prints out either you got it or it prints, I think my dog figured this out before you. And somewhere in here, it does a compare, which will compare the answer to see whether you put in the right answer. And you could read this and figure out what the right answer is, but what's easier is to just patch the code with NOPS. So it doesn't bother to do this compare, and it doesn't bother to do this jump. And then it reads something, but whatever you read, it prints the winning message. So you win without having to get the right number. There's many ways to defeat this game once you can cheat in a debugger, but knopping is probably the simplest. And so if you move forward in here and then step into puts, then you can see the call stack. So your inputs, and it'll show you that the kernel's up here. So you are one step away from the kernel. Anyway, if you step into again, now you're 2 steps in. So you can see that you're digging your inputs, and you can see the stack of places, the module you entered, then your inputs, then you're in some other module. So you'll see that that's the call stack, the call that got me here. And when you return it, the call stack gets smaller again as you return from some of these. So if you use one of your lab notes, you'll actually find the call stack to be far deeper as you use one of these more complicated programs. All right, you can run a run trace, and then it will really record everything it does, everything it changes in the registers and so on. So then you can actually go forward and you can actually go backward. But of course, this is really expensive and slow. It's got to be remembering a lot. So you wouldn't want to just do this all the time. But you can, in fact, do a run trace, you highlight some of the instructions, then you turn on a run trace, and now when you go through those instructions, you can go forward and backward completely. All right. All right, and so I did it here for that one, but I'm not going to do it live now because I've got more exciting, newer stuff I want to get to. Anyway, so, all right. Then you can also do trace into and trace over with these traces. And you can set a condition which will cause the run trace in a complicated if statement to have it stop and stuff. I've never used this complicated stuff, and I'm going to just skip through it kind of quickly. You should be aware it exists, but you aren't going to need to do it for any of the projects here. It's something you'd look up if you actually need it. Exceptions, however, really matter, and we use them quite a lot in the exploit development class. So when something happens that the program cannot do, it gets a construction it cannot do, then you have an exception. And you can then choose. Shift F7 will step into the exception. Shift F9 will just resume execution running the exception handler. And you can also step over. Normally, Shift F9 is the only thing I use here. It hits an exception and comes to the debugger. And if I want to let my program handle the exception, I press Shift F9 and it goes back to run the exception handler. All right. And that Normally in malware analysis, you ignore exceptions because you don't really care if the virus is crashing and you're not trying to debug it. Now, if you're a developer, exceptions would matter because they indicate a bug in your code. And if you're an exploit developer, they're really important because you can use them to take over the machine, because the exception handler is frequently vulnerable and you can modify the addresses in the exception handler. So causing an exception is in fact how you take over the machine. All right. So then you can patch code. Like say you can right click and fill it with zeros or nops or binary copy or edit, modify instructions one by one. You can fill with nops, which is what I usually do just to remove code so it will do nothing. And now, as we've done before, to save the compiled code, it took me a while to learn how to do it. You have to right click in the window that you've been modifying and then copy to execute all modifications save file. And that will copy all the modifications in that one memory segment. But you can't make multiple changes all over the place and save them all at once. The best thing is to save after every one change, or it gets very confusing. All right, and if you have shellcode is the heart of malware. When you have the ability to run some code on a machine, what you try to do is run shellcode, and you often try to get very small, very efficient shellcode. Shellcode typically calls home with a network connection to the command and control server, and then gives the command and control server a command prompt so they can execute code on the server. So if you want to analyze shellcode, there's a technique here you can use to do it in the memory map. There's a way to do it inside a debugger. I've read about this. I've never done it. In the exploit development class, we do develop shellcode, and the way I've always tested it now is by just writing some C code to test it. That's another way to do it. But you can do it inside a debugger, and it might be a way you wanted to analyze malicious shellcode. But normally, the only thing I would do to analyze shellcode is just find the IP address or the domain name in there and call that an indicator of compromise and use dynamic analysis to understand it. Anyway, there's a log, which is keeping track of everything you do. So that might be useful if something surprising happens. And you can run watches that will watch to see one value as it changes. That might be useful. You can see the values in the EIP or some other register here. And you can label things. This is more important in IDA Pro, but if you're analyzing a big piece, you can actually make user-defined labels that it will remember to refer to. You have a function, it starts out with some stupid name like just a number, and you can change that with a descriptive name of the function, and that might help you figure out what's going on. And there are plugins. Like Wireshark, OllyDbg is a framework, and you can write modules and write custom modules to do things, and there's a whole community of people writing more plugins. So here's one that will dump the process to a PE file. Here's one that will hide the debugger from debugger detection, because a lot of malware checks to see if it's in a debugger and then it doesn't run right. There's a command line version, and there's bookmarks, and there are many other ones out there. And you can write scripts. I've used a few of these for the Linux debugger GDB. That's how I made some really nice projects where students can attack my server, and my server automatically debugs the code and lets them see the debug code so they don't have to install any software locally, which is pretty nice. And you can do that with Olly and Immunity too. By the way, OllyDbg is the old product, and the code was sold to Immunity, which is a modern company that makes a more modern version of it called Immunity Debugger, which for all intents and purposes is exactly the same. And all the commands are the same and everything. So you can use either Immunity or Olly, and for all normal activities, they're just the same. But probably we should all just quit using all of them and move to WinDbg. And that's what I'm going to talk about later. But Olly is still easier to use, but WinDbg is getting better, which is why I got that letter from a gentleman at Microsoft, and I started looking at it again today. The newest version of WinDbg is getting much better, and I think it might be time to just abandon OllyDbg and Immunity entirely and just switch to WinDbg. All right, good. I'll give it a few more seconds. All right, let's see if I got the right one this time. That's the right one. Okay, good. Okay, if you press the minus sign, what's that? A backtrace. It shows you where the previous instruction was. All right. Which one lets you step back and see the values, like running time back? Okay, that's a run trace. That's what that is. All right, what feature shows you all the functions that are waiting for execution to resume? That's the call stack trace. So you know you're running Windows. Then if you're running 32-bit code on a 64-bit system, you're running the Windows on Windows environment. Then you launch your main routine. Then it calls a subroutine. So you're really running 4 things at once. But 3 of them are waiting for the one you're in to return. That's what the call stack is. All right. All right, which one will show you all the modules that were loaded before the current one? Okay, that's the log. And you know, Olly is really very powerful, but it's pretty old. So we got Erica and register. I know who that is. And Dubs, you have to tell me who they are if they want their points, unless that's close enough to the real name. All right. So I'm going to stop the recording and we'll take about a 10-minute break. We'll pick up at 5 after 7, and then I have quite a few things to tell you about the projects. So come back if you want to see that.